Hello everyone, and welcome back to another episode of F.O.A Maths. In the last video, we talked about some interesting perspectives that we can take on fractions. In particular, we saw that fraction multiplication was really just doing two different things at once. It wasn't just multiplying by a number, but it was actually basically a stretching and a compression, and that took us all the way back to where we started with this series. So it was kind of cool to see that. And we also saw that furthermore, we can not only think of fraction multiplication like this, but we can think of just fractions themselves like this, where if we, instead of viewing a fraction as a number, we view it as like an action, like for example, something we do to the number line and where 1 ultimately lands, we saw that we can think of fractions themselves as double actions. So then when we multiply fractions, we saw that we could think of about that as basically a combination of these actions. So these ideas are admittedly a bit abstract. They're harder to deal with, but I think it's an important idea to really grasp, an important perspective to get a hold of, because that's going to really allow us to understand things a lot better moving forward. So I do have some exercises today that's going to kind of help us get a little more comfortable with these perspectives that we introduced in the last video. So as always, go ahead, pause the video, try these out for yourself first, and once you've given that a good honest go, let's go ahead and do this together. Alright, so for our first question, this says, which of the following perspectives of 2/3 times 5/2 is not true? Alright, so we have 4 different interpretations of this statement here, and we need to determine which one is the incorrect interpretation. The first one is 2/3 times 5/2, that's going to be where 2/3 lands when stretching the number line by 5 and then compressing by 2. So essentially what we're saying is we're taking our 2/3, and that's somewhere on the number line, right? Very poorly drawn number line. And what we're going to do is we're going to stretch this number line out to be 5 times long. So now 1's like way over here, and 2/3, that's going to be, maybe like right there, for example. And then we compress that number line by 2. So that's dividing by 2. Right, so this is just a very rough sketch of what's actually going on. But this multiplying by 5, this stretching by 5, and compression by 2, this 2/3, where that lands, we're saying that's going to be the same thing as 2/3 times 5/2. And yeah, this is going to be true, because multiplying by 5/2 has that double action of stretching by 5 and then compressing by 2. So that's the multiplying by 5 and then the dividing by 2. So part A is definitely a true statement. For part B, it's similar, but it's just in the other order now, right? It's where 5/2 lands when stretching the number line by 2 and then compressing by 3. So it just kind of changes the order of how we're looking at this. We know that 2/3 times 5/2, that's the same thing as 5/2 times 2/3, right? It doesn't matter the order in which you multiply things. So if this order doesn't matter, we can equally think about doing this double action right here to the 2/3 as we can think about doing this double action right here to the 5/2. So it's going to give us the same thing. And so if we stretch the number line by 2 and then compress by 3, wherever 5/2 lands, that's going to be our resulting product. So part B is also going to be true. For part C, it says the action of stretching the number line by 10 and then compressing by 6. So you may be able to see where they get the 10 and the 6, because if we actually do 2/3 times 5/2, that's going to be 2 times 5 in the numerator, 3 times 2 in the denominator, and that gives us 10 over 6. So this is the stretching by 10 and the compressing by 6. But it's not where something lands, it's saying this is the actual action. So this goes back to what we talked about in the second half of the video, where we were talking about how we can actually just view a fraction itself as essentially being an action, where encoded into the fraction, the numerator tells us how much to stretch by, and the denominator tells us how much to compress by. So then we know that essentially by looking at these two fractions like that, we take our numerators, which is the 2 and the 5, so that's telling us how much to stretch, and then we combine those, right? So the 2 times 5, that gives us a total of stretching by a factor of 10. And for the denominators, we know that if we compress by a factor of 3 and we compress by a factor of 2, we can combine these denominators, and that gives us a compression by a factor of 6. So this part C also looks good. And for part D, this is actually taking a perspective we looked at when we first introduced fraction multiplication. So for this one right here, it looks like we have 2 of 3 pieces shaded, and here it looks like we have 5 of 6 pieces shaded. So right off the bat, you might think, well, this one isn't true because it's looking like the 5 halves. But where then did we get this 5/6 from? Did I just make up a number and so that was good? Well, what this actually kind of comes from is if we look at doing 2/3, and then the 5 halves, remember, we have to basically split a piece into halves, right? We have to split it into 2 pieces, but we're going to have to do that 3 times in order to actually get 5 of those pieces, right? So then we shade everything in. So this is the 2/3, right? 2 of those pieces of size a third, and this is our 5 halves, 5 of these pieces of size a half. And then what we can do is we can figure out the shaded portion that would be formed by this, and we would be good to go. But the key element here is to note that there are 6 pieces here, but these 6 pieces are basically spread out over 3 different holes, right? And so that's kind of the subtle difference here is we have these separations to actually make sure that these pieces are a size a half. Whereas here we don't have the separation, so these pieces are sizes of a sixth. So this would actually equate to being 2/3 times 5/6. So part D is the false one. All right, I hope that makes sense and that it gives you kind of a good idea of some different perspectives that we have on what one product of fractions can look like. Let's go on to part 2. All right, part 2 says, is just a true or false question. 7 times 3/5 can be described as splitting 7 into 5 parts and then taking 3 of those pieces. So we know that 7 times 3/5, one way we can interpret this is saying we are looking at a piece of size 3/5 and we're taking 7 of it, right? I mean, this is what we originally knew multiplication to be. If I do 3 times 2, I'm basically taking 3 groups of something of size 2, right? So here I'm taking 7 groups of something of size 3/5. And we know that 3/5 is the same thing as 3 divided by 5, and that's essentially us taking 3 and splitting it into 5 pieces, right? So we would be able to say with confidence that this is splitting 3 into 5 parts and then taking 7 of those pieces, but this looks a little bit different. It's saying splitting 7 into 5 parts and taking 3 of those pieces. So does that mean it's false? Well, not actually, because what we can do is we know that 7 times 3/5, that's the same thing as 7 over 1 times 3 over 5, right? And then, combining these, we get 7 times 3 in the numerator and 1 times 5 in the denominator. But what we can do is we can change the order of what we multiply, right? So this is really just 3 times 7 over 1 times 5. But then if I kind of split this back up into 2 fractions again, this is going to be basically 3 over 1 times 7 over 5. But 3 over 1 is just 3, so we get 3 times 7/5. So see, I essentially just exchanged the position of the 7 and the 3, because ultimately what we've done is, well, they're going to be multiplying anyway, so I'm just changing the order that we're multiplying them, which doesn't affect the result. Another way we can think about this in terms of kind of numbers and fractions as being like actions in and of themselves is, okay, if we think of 7 as being the action of stretch by 7, and if we think of 3 as being the action of stretch by 3, then essentially what we get is that because we're stretching by 7 and then stretching by 3, that doesn't change if we stretched by 3 first and then stretched by 7, right? So again, that gives a justification as to why I can change the order of them. But now that I've changed the order, it's a little more obvious that this is true, because the 7/5 is us taking 7 and splitting it into 5 parts. So that's right there. And then we're taking 3 of those pieces, right? 3 times that. So that's this piece right there. So we look like we are going to be correct. So this is going to be true. All right, let's move on to part 3. All right, so this one says use number line transformations to demonstrate the double action of 3 times 4/5. All right, so 3 times 4/5, essentially we want to look at the double action of multiplying by 4/5 and then see where 3 ends up. So what we can do is we can start with the number line. The first thing that happens when we multiply by 4/5 is the numerator tells us to stretch it by a factor of 4. So let's go ahead and stretch this number line by a factor of 4. So we keep 0 fixed, and the distance between ticks now increases to be 4 times as long. So that means before, the distance between 0 and 1 now gets expanded to be essentially the same as the distance between 0 and 4. We got 2, and we got 3. All right. And then we're going to compress by 5, because that's what the denominator is telling us to do. And I can already line up the 5, 10, and 15 because we know that 5 divided by 5 will be 1. 10 divided by 5 will be 2. So this gives us kind of like some benchmarks in order to graph this easier. Okay, so where does 3 end up? So 3 lines up somewhere between 2 and 3. All right, so 3 got stretched out and then it got compressed, right, along with the rest of the number line. So let's see if that is actually true or not. So 3 times 4 is 12, and then we have our over 5. And 12 over 5, that is 2.4. So it's somewhere between 2 and 3, yeah. So I probably could have drawn this a little more accurately, but yeah, 3, it lands between 2 and 3, and that's where 2.4 is. So we see that this works. And once again, we could try this for other numbers, right? We could look at what is 10 times 4 fifths, all right? Well, we know that that's going to be 40 over 5, which is 8. And if we look at where 10 lands, yeah, 10 lines up with around 8. So this is kind of a nice visualization for what the action of multiplying by 4 fifths is. Again, it's a stretching and it's a compressing. And for extra practice to get used to this idea, just make up a bunch of different fractions that you can multiply by. Look at how those actions affect the number line. And once you get comfortable with it, you're good to move on. Let's go on to the fourth question. So I'm seeing right now I mislabeled this as number 3. This should be number 4. And it says, describe the triple action that's represented by negative 5/3. Okay, so this is talking about a triple action now. So that's kind of interesting. So one thing that we're going to need is, let's just start with what a negative number does. So we're going to have to go back to the videos where we talked about perspectives on negatives. And essentially we saw that one way we could view a negative, right, like negative 2, for example, was as negative 1 times 2. So essentially, we are thinking about this negative as being an action where we flip it, right? So the negative is the flipping action. But we're doing this to negative 5/3. So if we do negative 5/3, this is really negative 1 times 5/3. So now this negative 1 is our flip. But now we have the 5/3 as well to deal with, right? So the 5 in the numerator, that's a stretch by a factor of 5. And the 3 in the denominator, that is a compression by 3, right? So if we consider this number as basically being an action, right? Like, so if we were to multiply this number, then essentially we are doing 3 different things. The negative says we're flipping it. The 5 says we're stretching by 5. And the 3 says we're compressing by 3. If we flip our number line, stretch by 5, and compress by 3. If we do all these things to our number line, negative 5/3 is where 1 will land. Right, that was kind of our way that we could think of this negative 5/3 as actually being an action, because if we think about where 1 lands, 1 will basically land on the number that describes what happened to the whole number line, right? So 1 is landing on negative 5/3 because what happened to the number line is we applied the negative, we flipped it, we stretched it by 5, right? So that's the numerator of 5, and we divided by 3. That's the denominator of 3. That's the compression, right? So we know that negative 5/3 is 1 times negative 5/3, which is 1 times negative 1 times 5/3, right? So that's our flip action, that's our stretch action, and that's our compression action. So that is a triple action, all represented within this one negative fraction. Let's go on to the last question. Okay, so question 5 says, justify y when multiplying by a proper fraction. So that's where the numerator is less than the denominator. So like, for example, 4 fifths, 1/10, 3/17, right? Those would all be proper fractions. So it's saying, why is it that when you multiply a number by a proper fraction, you get a smaller result? All right, so for example, if I do 3 times 4 fifths, I'm going to get 12 fifths, which is 2.4, which is smaller than 3. So basically I took 3, multiplied by 4 fifths, and the result was less than 3. If I take 20 and I multiply it by 4 fifths, okay, what am I going to get? I'm going to get 80 over 5, which is 16, Once again, that's less than 20. Right, so it's saying that whatever I start with, when I multiply by a proper fraction, regardless of what the proper fraction is, I'm going to be getting an answer, a product, that is smaller than what I started with. And then it also says, justify why when multiplying by an improper fraction, you get a larger product. So for example, let's say I had something like 7/2, right? That's an improper fraction, or 5/3, that's another improper fraction. So if I do, let's say 3 times 5/3, okay, what am I going to get? I'm going to get 15/3, which is 5, and 5 is bigger than 3, so the product, right, the product is bigger than what I started with of that 3. Or if I do, let's say 7 times 5/3, okay, what am I going to get? I'm going to get 35/3, which is 11.6 repeating, which is, once again, this product is bigger than the number I started with. So there's this pattern where if we multiply by a proper fraction, we're going to get a smaller answer than what we started with. It's going to basically make the number smaller. If we multiply by an improper fraction, it's going to make the number larger, and we need to justify why this is the case. And there's different ways of doing this. One way that you might kind of reason with it is that we know that improper fractions are bigger than 1. So if I'm multiplying by 5/3, I'm multiplying by something that's bigger than 1, so that kind of makes sense that it's going to make it, stretch out a little bit, right? But if I'm multiplying by something that's smaller than 1, right, 4/5, proper fractions, they're between 0 and 1, then we're kind of like taking a smaller piece of this 3, or a smaller piece of this 20, right, and we're making it smaller. So that's kind of one way to think about it. But I think that an even better way to think about it is, we know that fraction multiplication is a double action, and this is going to be really useful. So if I think of 3 times 4/5, right? So if I multiply by 4/5, what am I doing? I am going to be stretching the number line by 4. So this is a stretch by 4, and then a compress by 5. But the thing is, the compressed by 5, that is more compressed than we stretched by, right? So that means our final result, this is going to result in more compressed than the original. But on the other hand, let's say I multiplied by 5/3 like I do here, right? So the numerator is a 5, so I'm stretching by 5, and I'm compressing by 3. But the thing is, here, the stretch, there's more stretch than we went compressing, right? So that means our overall result is that it was more stretched than the original. And this is really cool, because by noting that fraction multiplication has both this stretching and compressing part, we can basically see which part does more. Is the stretching stronger, or is the compression stronger, right? And so for proper fractions, since the stretch, which is the numerator, is smaller than the compression, which is the denominator, what we get is that when we apply this double action, we're going to get a number, well, that ultimately got more compressed. So that means that number ultimately is smaller. So that means any number that you put into this multiplication by proper fractions, that's going to go to a smaller spot than when you started with, because the overall action is a compression to the number line. And then it's just the opposite for improper fractions. Okay, so for improper fractions, since the stretch, or the numerator, is larger than the denominator, which is the compression, then we get a resulting stretch, right? More stretch than compression means overall we've stretched it more. And that means by multiplying by an improper fraction, basically any number that we put into that, it's going to go to a bigger number as the resulting product. So I think this question number 5 is an awesome example as to why this is such a useful perspective, because it actually gave us a really strong and robust justification for this property we see when multiplying by proper fractions and multiplying by improper fractions. So I hope you found that useful, and I hope you're feeling more comfortable with this perspective on fraction multiplication and really what fractions are. We're going to be using this idea several more times, so if you're still not feeling great with it, make sure to do more practice. Maybe leave some questions if you're confused about something. And yeah, that's going to do it for me today. But until the next video, you have a good one, you stay groovy, and I'll see you then. This stock video is definitely proof that birds are just government drones. Look how it's sneaking its suspicious little head out from
Bo maths.